Hello everyone, Ritu ma'am here. So today we will take the next topic of chapter hydrocarbon from class 11th and it is aromatic hydrocarbon. So as we know that hydrocarbons are classified into three categories. The first one is saturated hydrocarbons, second is the unsaturated hydrocarbons, and third is the aromatic hydrocarbon. So here we will take aromatic hydrocarbons in detail. The aromatic hydrocarbon are also known as the arenes. These are also known as the arenes. These are known as aromatic hydrocarbon because of the presence of pleasant smell in them. They consist pleasant smell or pleasant odor. The word aromatic is derived from a Greek word aroma. Aroma is a Greek word which means pleasant smelling. So because of the presence of pleasant smell, they are known as the aromatic hydrocarbons. Now, as we know that aromatic compounds are the third category of the hydrocarbons. They have some specific qualities. One thing that most of the compounds which consist benzene ring are considered as the aromatic hydrocarbons, right? These are highly unsaturated compounds. Aromatics are highly unsaturated compounds. They consist benzene ring, and there are some more compounds which do not consist benzene ring, but still they are aromatic in nature. So we have two types of aromatic hydrocarbons. We have two types of aromatic hydrocarbons. First is the Benzenoid aromatic hydrocarbons and the second is non-benzenoids. So benzenoid, that means which contains benzene ring. While non-benzenoid, that means they are aromatic but they do not contain benzene ring. Right? So we have some examples. For example, benzenoid example, just like simply we have benzene, and all substituents of benzene are under the category of benzenoid. Like toluene, this is benzene, this is toluene, naphthalene, right, and many more, right? And in non-benzenoid, which do not have benzene ring but still they are benzene in nature, aromatic in nature, I'm so sorry. So like this is furan, this is furan, this is thiophene, right? These are non-benzenoids, right? I'm taking one more. This is cyclopentadienyl anion. So these are the non-benzenoid aromatic hydrocarbons, right? So now we take their nomenclature and isomerism. Here I am taking nomenclature and isomerism. As nomenclature is you have already studied in the previous chapter, so here we will take it in brief. So let's start. So you have to remember that all 6 hydrogen atom in benzene are equivalent, right? They all are equivalent. So whenever we do the substitution reaction of benzene, there will be formation of single substituted product. That means mono substituted product. There will be formation of only one type. There will be formation of only one type of mono substituted product. When we replace two hydrogen atom in benzene with similar or different atoms or groups, then there will be possibility of formation of di-substituted product, and the possibility of formation of di-substituted product will be at 1,2 position, at 1,3 position, or at 1,4 position, right? So 1,2 position means, like I have this one, this is benzene, right? If we do the substitution reaction with the methyl group, then I replace one hydrogen from the methyl group, then this is the toluene, right? And this is mono substituted product. This is, you can write toluene or methyl benzene also, the name of this compound, right? So if I further do the substitution reaction, right, I remove one hydrogen from here and I add one CH3, then the coming group, the CH3, this coming group have three possibility that it can attach. Like this is position 1, this is 2, this is 3, this is 4, this is 5, and this is 6. So there will be three possibility for the formation of di-substituted product. The first one is that CH3 can be attached through 2 or 6 position, because both the position are similar. So 1, 2 or 1, 6, they are the same compound. If CH3 attached to position 2 or 6, they will be same, because this is one carbon and they both are adjacent to the first carbon, right? So let it attach to this position or this position. So what will be the product if CH3 group attached to this position? It will be CH3, CH3, right? And the name of this compound is 1,2-dimethyl benzene, right? This is one position, this is two position, this is 1,2-dimethyl benzene. This is the IUPAC name, right? But the journal name is orthoxylene. When 2-methyl group is attached to benzene ring, then the compound is known as the xylene. And when the group are at the position of 1, 2 or 1, 6, then the position is known as the ortho, which is represented by O. This is ortho product. Ortho product, right? This is ortho product. So this is the first possibility, right? Now we check the second possibility which can be occurs. So the CH3 group can be attached now at 3 position. So when it attached to 3 position, the third position, then what will be the product? I am taking the second possibility. When it attached, this is the reactant. When one hydrogen replaced to CH3 group and it attached to third position, then the compound is again dimethyl benzene, but now it is 1,3-dimethyl benzene. Previously we have taken 1,2-dimethyl benzene, right? And this position, the 1,3 position, is known as the meta. This is the meta form, and because this compound is xylene, I have already told you that whenever 2-methyl group attached to a benzene ring, then the compound is known as xylene. Xylene is the common name of the compound. So this will be meta-xylene. Meta because this position, 1,3 position, shows the meta form. So this is the meta product, right? So now the next possibility. So benzene have 3 possibilities for the formation of disubstituted product. Now the third one. What will be the last possibility? Now we have already taken second and sixth position, third position. Now we take the fourth position. Okay. One more thing, the 3 and 5 position also similar. This one and this one is also similar. So you can see the, if I am writing this one at the third position, or if I write in this way, then also it is meta product, right? Meta doesn't mean that the compound, the group or the atom should be attached to this position only, right? So this means that it should be attached to the carbon which is at the position of third from the first one, or at the position of 5 from the first one, right? So this is the meta form, meta product. Now the last probability to form the compound is this one, when the coming group attached to just opposite to the one position, which is the fourth position. So the compound formed is CS3. This will be just opposite, at the just opposite position, and now this form is known as the para isomer or para form. So this will be the para-xylene, and in IUPAC form I can write it. This is 1, this is 2, this is 3, and this is 4. This is 1,4-dimethyl benzene. So this is the para product. So in this way we can see that when we do the di substitution of benzene, that means when we already have the mono substituted product of benzene and we do the further substitution, then we will get 3 type of isomer with respect to benzene: the ortho product, the meta product, and the para product, right? Now come to the structure of benzene. I think this is clear to everyone. Now come to the structure of benzene. So structure of benzene. See, benzene was first isolated by Michael Faraday. Michael Faraday was the first scientist who have isolated benzene in 1825. Isolated by Michael Faraday, right? So on the basis of the studies, the molecular formula which comes out for the benzene is C6H6, right? This formula C6H6 indicates that this compound is highly unsaturated. Why? This indicates the highly unsaturation in the benzene, because if we check the corresponding alkane to this compound, the corresponding alkane will be C6H14, right? That means it consists of 8 hydrogen less than the its corresponding alkane, right? So that means it consists highly unsaturation in the compound. One more thing, this compound, this formula do not relate with the alkane, because alkanes are CnH2n plus 2. They do not relate with alkenes, which is CnH2n. It also do not relate with alkyne, which is CnH2n minus. So it shows C and HN, right? So it do not relate with any one of them. That means it shows that there is unsaturation, but it has some different structure. One more thing, that it has unique properties and unusual stability. It is highly stable, which shows that it has some different structure, and it took several years to study its structure, right? So benzene was found that it is one of the most stable molecule, and it found that when we do the reaction with ozone, right? When we do the reaction with ozone, then what happened? It forms triozonide. So formation of triozonide shows that there is presence of unsaturation. It consists 3 double bonds. It shows presence of 3 double bonds, right? One more thing, when we do the reaction with hydrogen, then there it shows the addition reaction. When we do the reaction with hydrogen in presence of nickel or platinum as a catalyst, then it shows formation of cyclohexane. It shows the formation of cyclohexane, right? It shows the it shows the presence of unsaturation in the compound. Now next we can see that if we do the reaction with bromine in CCl4 solution, in CCl4 solvent, then it do not show the addition reaction. However, it shows the substitution product. It shows the mono substitution product. That means if I have C6H6, I react it with bromine in presence of carbon tetrachloride, it should form C6H6Br2, right? But there will be no formation of this compound. That means the addition product is not formed when it react with bromine. However, when it treated with bromine in presence of FeBr3, then there will be formation of mono substituted product, which is bromobenzene. So it shows substitution reaction more frequently as compared to addition reaction. This is substitution reaction. So these reactions shows that this has some unique property, and it somehow have different structure as compared to normal alkene, right? So on the basis of these observations, there was a scientist, Auguste Kekulé. Auguste Kekulé was a scientist who in 1865 proposed a structure of benzene, and he showed that there should be a cyclic arrangement of 6 carbon atom with alternate single and double bonds, and 1 hydrogen attached to each carbon atom. That means we have 6 carbon in the form of cyclic form. Then each carbon should be attached through the 1 hydrogen atom. That means he showed such type of a structure for benzene, that there should be, this is carbon, this is carbon, this is carbon, carbon, carbon and carbon, and this is the cyclic form. And he showed that with each carbon 1 hydrogen is attached in this way, and there will be single double bond on alternation. I can draw it again in this way, right? Single double, and with every carbon, with each carbon, hydrogen is attached in such a way, which in short can be written as like this, right? So this was the Kekulé structure. It was, the name was given on the basis of Kekulé, who has discovered the structure. The Kekulé structure indicates that there is the possibility of 2 isomers when we react with bromine. That means he considered that when we react it with bromine, then there should be formation of 2 isomeric 1,2-dibromobenzene, right? So however, if we want to draw, he suggests that when we react with bromine, there should be formation of this one, which is 1,2-dibromo. In this way, then it is attached to the single bond, and the other form is this one, in which it is attached to the across the double bond. This should be the product. According to both the name of both the compound is 1,2-dibromobenzene. So according to Kekulé structure, when we do the bromination of benzene, there should be formation of this isomeric product, two isomeric product. But actually in reality there is formation of only one ortho di-substituted product. So this problem was overcome by a suggestion of Kekulé, that he found that there should be concept of oscillating nature of double bond in the benzene. He suggests that there should be some oscillating nature of double bond. Oscillation nature, that means the double bond can be oscillate from its own position. That means he suggests that this should be the structure. The double bond oscillate from their position, and that's why there should be formation of only single di-substituted product, right? So this was the explanation from the side of Kekulé. But further study shows that Kekulé was failed to explain the unusual stability of the benzene, and further study showed that this structure can be explained on the basis of resonance. So now we take the resonance and the stability of benzene. So here I am taking resonance in benzene and its stability, that why it is so stable. So according to, we know that according to Kekulé, he gave the above structure, which is known as the Kekulé structure. But actually, when we take the benzene and we do its resonance, then it is found that it is the resonance hybrid of two structure, which is structure A and B. It is a resonance hybrid of these two structure, and this is the resonance hybrid. So this is the actual structure of the benzene. This circle in the benzene shows that that electrons can be oscillate from one position to other, and it can move throughout the circle, throughout the cyclic form, throughout the cycle which is present in the benzene, right? So it shows that the orbital overlapping in the benzene, and that's why there will be possibility of resonance, and that's why it exists in the form of this resonance hybrid instead of the structure A or B, which I have given by Kekulé. Now we take the proper orbital overlapping in the benzene. So let's check it. So first of all, we all know that because of the presence of double bond, it consists sp2 hybrid orbital of carbon, right? There is 6 sp2 hybridized orbital of carbon. So let's make it. So each sp2 means there is 3 sp2 hybridized orbital, right? Means there should be 3 lobes. So in each carbon there are 3 sp2 hybridized orbs. So this is first carbon, okay? It overlap with the neighboring one in such a way. This is 2. Three, 4, 5 and 6. So in such a way 1, 2, 3, 4, 5 and 6, right? Numbering you can given from this side also. So by the overlapping of sp2 hybridized carbon orbital, there will be formation of sigma bond. This is sp2 hybridized orbital. This is also sp2. In the same way, sp2, sp2. This is sp2 hybridized orbital. Again sp2 hybridized, sp2. That means out of 3 sp2 orbital for each carbon atom, the 2 is used up in the for the formation of sigma bond, in such a way that we will get 6 carbon sigma bond, right? That means 1 sigma. This is, let's see, this is 6, sorry, this is 6. This is 1 sigma. This is sigma bond. This is also sigma bond, sigma bond, sigma bond, sigma and sigma. So 1, 2, 3, 4, 5 and 6 carbon sigma bond. Now because the formula is C6H6, so there is presence of 6 hydrogen also. Hydrogen is 1s1, that means they have spherical form, they have s orbital. So the s orbital again do the head-on overlapping and form the 6 sigma bond, right? So there will be 6 CH sigma bond. This is the first one. This is the second conclusion. So that means, let's see, this is sigma bond, sigma, again sigma, sigma. So this is s orbital of hydrogen, right? So in this way we can write that this is the sigma bond formation of the benzene, right? Now we have to show the pi bond formation in the benzene. So the unhybridized p orbital, when there is, this is C6, that means 1s2, 2s2, 2px1 and 2py1. So when s go to its higher excited state, then this s and 2p, they combine together, undergo the hybridization. So there will be there is one unhybridized p orbital for each carbon atom. There is presence of one unhybridized p orbital at every carbon atom, right? So each carbon atom has 6 unhybridized, sorry, 1 unhybridized p orbital. That is total 6 unhybridized p orbital. These are the unhybridized p orbital, and you have to remember that the pi bond formation is always formed, the formation of pi bond is always done by the unhybridized p orbital, So they are close enough that they can form the literal overlapping and they can form the pi bond. So there are possibility that just like they can overlap with the near one, right? So it just like we have this orbital, so it can overlap with this orbital or this orbital. So it has two possibility. It can attach, it can overlap with this one or this one. In the same way, this can overlap with this orbital or this orbital. So in such a way, there are possibilities of forming 3 pi bonds by overlapping of p orbitals of, I'm showing you. So this is the cycle of benzene, right? This is the cyclic form. At each carbon there is presence of unhybridized p orbital, right, which I have already shown you in such a way. Now I'm giving numbering here. This is 1, 2, 3, 4, 5 and 6. 1, 2, 3, 4, 5 and 6. So let's see. 1, the p unhybridized p orbital at 1, it overlap literally with the unhybridized orbital which is present at the second position. In the same way, 3 can overlap with the fourth one, 5 can overlap with the sixth one, right? The other possibility is that 1, it may overlap literally with sixth carbon, unhybridized orbital at sixth carbon, fourth with fifth, second with third. So in such a way, there is 2 type of possibility of benzene ring. So this is the actual form because of which we can say that it is the combination of 2 structure. It is the resonance hybrid of 2 structure, right? Because of the basis of these overlapping which I have shown you here. So now we can conclude the structure that I am concluding the structure. So I have this form, right? So that means the overlapping area. The overlapping, this can be represented in the form of 2 rings, right? 2 rings of electron clouds. That means the possibility is here, 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 here. That means the possibility of formation of overlapping or overlapping is across the complete ring. That means there is presence of electron clouds, one above and one below to the plane of hexagonal ring. That means we can show it in this form. This is the hexagonal ring, the cycle, and this is the ring, electron clouds, right? This is the electron clouds, one above and one below. Because of these are the electron clouds, right? So that's why we show the benzene in this way, that by inserting a cycle in the benzene ring, right? This is the benzene and we write a circle in the benzene ring because we want to show the electron clouds which occur because of the overlapping of the unhybridized orbital present at each carbon atom. So because of the presence of these delocalized pi electron in benzene, it makes benzene more stable, right? Because there is the more possibility of delocalization, it creates more stability. It gives more stability to the benzene ring. So here it is all about the structure of benzene and the idea of aromatic compounds. I think this is clear to you. So thank you so much for watching the video.